good morning, evening, afternoon, or whatever time of day it is where you are right now while you're watching this video. In this session, we're going to talk about two or three things here. In particular, the information that I'll be using is primarily coming from the NCCER Section 3. And if you'll notice on your screen, I have week 4 up here. That's what this video is talking about. And notice that we have the usual suspects overview. I'm going to put this video that I'm doing right now that you will soon be watching right here. Here's the instructional resources for week 4, and I want you to read this. This is this. I brought this up not because you can't read, it's just because I want to go over some things to make sure you understand how some of the information in here relates to this assignment. So, for instance, we're going to be talking about surface area. Well, let me read the objective. Describe the weight bearing and flotation properties of different soils. Explain how soil characteristics, I'm reading over here where my arrow is. Explain how soil characteristics affect machine performance and describe how soil conditions can affect trench safety. So I bet we could talk a little bit about those things, those three things right now without having to read anything out of here. But let's see what they're going to do these things to meet these objectives. One of the things we're going to have to know how to do is to find the surface area of something. In this case, it'll be a rectangle. And maybe you had this in your certificate programs, and maybe you have been taught this in laying out a pad or whatever, but it's length times width. That gives you the square feet, inches, or whatever it is that you're trying to find the surface area of. Now, I want you to think about the term flotation. I'm not there yet, but I'm going to get there. But think about what keeps a dozer, the difference between a dozer, a wide tract, especially dozer going across against a muddy surface area. What keeps that dozer from getting stuck versus going across that same muddy area in a car or a pickup? Well, it's surface area. The tracks on a dozer have a lot of surface area. The dozer weight at any particular point on that dozer, is like 2 or 3 pounds per square inch. But now, don't go putting your arm under the tracks, because when you take away some of the contact with the ground, all of that weight's going to go toward that arm that you used to have that's laying there under those dozer tracks. What I'm getting at, snowshoes. Why are they so wide? Why are they wide like a tennis racket? Well, because they want you, that keeps you on top of the snow because of the surface area. If you had ice skates on, you can go right through the snow and down to the ground, probably. So that's flotation, and I want to get that out there because I want to get you thinking about how to find the area of anything, the surface area. So we went through the objectives here, and I want to talk about. Just want to mention this about these three. It says operators must know how to use the different types of heavy equipment to overcome problems caused by different soil characteristics. So 3 important characteristics that you need to keep in mind are the weight-bearing capacity. How much weight will that soil bear per square inch of whatever it is you've got driving over it. So that's the weight bearing capability of the soil. And we'll get to a chart on that here in just a minute. The other thing is the amount of traction a piece of equipment can get on the soil. Now the traction is it involves the weight of the equipment and the friction between the either tracks or the tires and the surface that you're on. The final, or the third important thing to understand is the resistance of the material to excavation. Now, they didn't mention rolling resistance. That's also another resistance, but what they're talking about here is wet clay. If you've ever dug it with a backhoe or an excavator, you know it is hard to get a full bucket out of there without lifting the rear end of the excavator off the ground. That's the resistance to digging it. We'll touch on that before we leave this lesson today, or tonight, whatever it is. So this section here, and you could be following along with me if you want. I don't, like I said, I know you can read, but there's some things I want to point out. So weight bearing and flotation properties. It's important to understand the relationship between the equipment and the weight bearing capacity of the soil on which the equipment is used. So let's talk about weight bearing specifically. The weight bearing capability of soil is how much weight it can safely support. It is related to the soil density. So when a soil density is low, meaning it is not well compacted, its weight bearing capacity is low. Compaction increases a soil's weight bearing capability and makes it more stable. Now, let's just scoot over here to the right. Look at Table 8 that lists some weight bearing capabilities of different soils. This is rock shattered, semi-shattered, probably gravelly, different shapes and things like that. Well, it has a weight bearing capacity of 70 pounds per square inch. Okay, so if you had something that had a surface area of 104 square inches, and if it would hold up 70 pounds, what would that be? To find that, you would take 70 pounds and divide it by 104 square inches. So that would give you the PSI, the pounds per square inch. Look at rock, solid rock, 350 pounds per square inch before you sank, if you ever did sink into it. And here's some dry clay, 55 pounds per square inch. Here's some medium dry, 27. Real soft clay, won't hold much up per square inch. Gravel, and it says cemented, that's gravel that has fines in it, and those fines act as binders, so it'll hold up a good bit of, it has a pretty strong weight-bearing capacity, 110 pounds per square inches. And then compacted sand, 55 if it's dry, and sand that's clean and dry, but not compacted. See, it drops down to 27, and of course quicksand won't keep much at all afloat. You certainly can't walk through it. So that's just going over something that's giving you some samples of different kinds of soil and their weight-bearing capability in pounds per square inch, are often referred to as PSI. So I have a note to go that this is probably going to continue. Measured in terms of, let me read this. Reducing tire pressure can also, weight bearing capability is usually, it's hard to keep up with the flow, measured in terms of pounds per square inch, or PSI, but it can be measured in any terms of weight per unit measure, such as pounds per square foot. The abbreviation PSI means the number of pounds that the soil can support on 1 square inch without sliding, excessively deforming, or collapsing altogether. Figure 22 illustrates the concept of pounds per square inch of pressure. In Figure 22A, a 200-pound person stands on 1 foot on a block of wood that is 1 inch square. The surface area in contact with the ground is 1 square inch, so the ground under the block is supporting 200 pounds. I'm going to that figure in a minute. In Figure 22B, the same person is standing that weighs, what did they weigh? The same person is standing with each foot on a 1 inch cube, so the ground under each cube is supporting 100 pounds per square inch. And the way I got that is that guy weighed 200 pounds. It says that somewhere up here, right there. So it's 200 pounds. That is the total weight, and divided by the surface area, which is 2 square inches. This same concept may be applied to heavy equipment because the total weight of the machine needs to be supported on the area of the tires or tracks in contact with the ground. When the weight on the tires exceeds the weight-bearing ability of the soil, the vehicle sinks into the ground until the pressure between the tires and the ground is equal. Now, let's go to Figure 22 and see what they're talking about. Here is, now I can't do this anymore. So this person weighs 200 pounds and he's standing on 1 square inch. So this is holding up 200 pounds per 1 square inch right here. Now look at this person. He weighs 200 pounds. So this person is standing on 2 square inches. So it's 200 pounds divided by 2 square inches. So this soil that this person is standing on has the capability of holding up 100 pounds per square inch. Now while we're down here looking to figure your surface area, you're going to take, this is a sample, and this sample, the same sample, is used in your week 4 assignment. So pay attention here. The tire itself is 13 inches long. The width of the tire is 8 inches. So to get the square inches of this tire, let's see if the book is doing it the way I am. It may not be. Well, anyway, so this will be the length and this will be the width, let's say. So the whole deal is a rectangle. So if you take 13 inches, multiply it times 8 inches, you're going to get 104 square inches of surface area on a single tire. Now, if you're on a 10-wheeler, you're going to get 10 times that because you have 10 wheels on the ground. So you're going to have 104 square inches multiplied times 10 equals 1,040 square inches. So that's going to hold up a good bit more than just talking about a single tire. Okay, now it all of a sudden goes into digging resistance, and I'm not sure let's talk about it real quick. I brought it up. What is this? Let me make sure. We've talked about this, weight bearing. We read all of this. We talked about flotation, did we not? Yes, divided by 2. Ability of a tire track to support the machine's weight on ground is called flotation. It's considered the total weight of the machine, including its payload. In other words, how much does the machine weigh plus whatever it's carrying, the contact area in square inches of the tires or tracks on the ground. The weight-bearing ability of the ground. The total weight of the vehicle is divided by the total contact area. Remember a while ago we ended up with 1,040. So in this case, the total weight of the vehicle, which could be 54,000 pounds, is divided by the total contact area of the tires, which in our case is a total of 1,040. Our tracks with the ground to determine the pressure of the machine on the ground. If this pressure is greater than the load carrying ability of the ground, the equipment will sink. Larger tires improve flotation because more tire surface is in contact with the ground. Now, what we're doing is we're coming up with a formula. So the total weight of the vehicle to get the pounds per square whatever, in this case inches, you take the total weight of the vehicle and divide it by the total contact area, which is 1,040, of the tires or tracks with the ground to determine the pressure on the machine on the ground. So if the machine did weigh 54,000 pounds, how can I lose a calculator in such a short time? Did I just put it somewhere? Let's get out the trusty phone. And just as hypothetical, what we're doing here, we have 54,000 pounds, hypothetically, 2, 3, and it's on a surface area, total surface area of 1,040 square inches. So we're going to get a weight per square inch. So 54,000 divided by 1040 equals 51.9. So essentially this would hold 52.5 pounds per square inch. Now look down here. Would it be good for this soil right here? No, not this one right here, because it's 52 pounds per square inch, and that's a little bit close to what this soil will hold up. Now, if it was cemented gravel that was cemented, we would be okay with weight-bearing capacity of 52 pounds per square inch. So now you see what we have done to get the pounds per square inch on a gravel, and then compare it to its rating, this type of soil, the pounds per square inch. So we took 54,000 as the total weight of the vehicle, divided it by the total contact area, which was 1,040 square inches, for all 10 tires. That gave us this number that I just lost. That gave us this number of 52 pounds per square inch, because we took total weight divided by total surface area. So there you have it. That's you will be doing that. Now, we got down here, we talked about this, and it's hard to keep the flow going in this thing. So let's see. Table 8 shows the approximate weight-bearing capability. We've talked about that. Weight-bearing capability is usually measured in terms of pounds per square inch. I think we talked about that. And it could be pounds per square foot if we want it to be. So you want it to hold the soil, to hold it up without sliding, excessively deforming, in other words, rutting, or just completely collapsing. And here's where we talk more about the surface area in contact with the ground. It's 1 square inch. That was at example 22. I want to make sure I covered the flotation. To find out, to me, flotation is just keeping it on top of the ground. And we came out with 21.9, and we decided that we would be okay if we was on a soil. 55 would be cutting it too close. What could we do if we had to go across this 55 pounds per square inch? We could put bigger tires on it, for one thing, right? We could increase our surface area by putting wider tires on it. Okay. Moving on, here's where we found the square inches of the surface. Let's read about rolling resistance. We're eventually going to have to do some rolling resistance calculation. It's the resistance of the tires to movement. If you've ever driven across what I call and is called elastic soil, that is where the soil deforms and makes a rut. However, once you get past that rut, it comes back to even with the surface. But there is, look at this tire. You can see that it's down a little bit. So this little area right here, if it's going in this direction, is where you get rolling resistance. It stays in front of that tire. It's like a wave in the ocean. As long as that weight is on that tire, this resistance is going to remain. So that's where you get your rolling resistance. The road surface flexes, so the effect is that the vehicle is always going uphill. It reduces your speed. It adds I want to say imaginary weight, because it doesn't increase the weight, but there is a chart that will tell you that your rolling resistance is equal to adding this many pounds more to the existing weight that you have. Now, let's see if we're going to get to that point here pretty quick. There it is. There's your chart of rolling resistance. Here is the soil samples that you're on, your surface. And this is the kind of tires, we'll assume radial tires. And this is if it's track. We're not going to bother with track because, see, you don't get little to any resistance with when you're in a dozer, because the surface area is much, much greater. So we're going to stick with this figure right here. The rolling resistance percentage increase in perceived weight. That's the only way I can think of it, because they came up with a formula that we'll be using, and this table in conjunction with this table that will be, I can't use that. That's not right. I'm going to use this one. This will keep us more realistic with a bias tire. Let's use this. So this is the surface. Very hard, smooth concrete, cold asphalt or dirt surface with no penetration or flexing. In other words, it's not doing any of this. It's sitting on top of the pavement. No resistance, really. So on a hard surface, cold asphalt or dirt with no penetration or flexion, you only get a 1.5% resistance. Now, I'll get to what that means later. This 1 and 1.5 becomes a factor. If you remember what factors are, there's something you multiply to something that reflects an additional restraint of some kind. Remember in Maybe you don't. You haven't had it, so you can't. But in hydraulics, if you took that course, there was a force multiplication, and you could get a factor that you could use of how much more or less when you increase the size of a piston in a hydraulic system, you get what's called force multiplication. In this instance, you're going to get some resistance. So going down through here, smooth, firm, rolling roadway with dirt or light surfacing, 3%, that's getting up there. That's fairly regular maintained. But look here, dirt roadway, rutted or flexing under load, little maintenance on the road, soft under travel, no stabilization. In other words, they haven't added anything like, what is that, potash or lime or other stabilizers to it. So you get an 8-inch penetration. In other words, it's penetrating 8 inches right here. So that's creating quite a bit of resistance. And as you can see, it's creating a 20.8% resistance. So we'll round that up to 21 when we get into calculations to calculate how much more. So where did I quit? I just jumped in here, didn't I? Let's read this. The rolling resistance is the resistance of the tires to movement. You have probably experienced having your personal vehicle sink in mud or snow. In this situation, more power is needed to move the vehicle. The deeper the tires sink, the more power is needed to move the vehicle. Thus, this increases rolling resistance, and it seems as if the vehicle is always going uphill. There's a question, and that's the answer to it. Tires do not need to sink for the vehicle to experience rolling resistance. When the road surface flexes as the vehicle moves over it, as shown in figure 24 right here, the effect is the same as sinking. Rolling resistance is measured in terms of percentage of the machine's total weight. In other words, weight of the machine plus the weight of the payload. The effect of rolling resistance of 20% is as if the vehicle is towing an additional percent of, help me, an additional percent of its weight. In other words, if it weighs 54,000 pounds and its rolling resistance is 20%, you would take 54,000 multiplied by 1.2, and that would give you the total resistance in the form of additional weight. In other words, it would tell you how much your machine should be considered total weight now with adding in the rolling resistance. So 54,000, as I said earlier, with a rolling resistance of, what's it? Going back and forth between glasses and things of that nature, of 2% down here. It was 20, so that would be 1.20. So take 1.20, which is about the same as 1.2. Let's see what that does. Clear it. 1.20 times 54,100 equals. Now we're looking at 64,800 total pounds. Now, just to verify this, let's take 54,000. Let's keep that 64,800 in my mind. If as a group we can, I'll just write it down. 64,000. 64,800. So that's what it's doing now, as opposed for the rolling, by adding the rolling resistance. Multiply 64,800 times 0.2, which is 20%, times 0.2 equals 12,960 plus 54,000 equals, I don't know, I hit something wrong there. Hold on. Let me clear that. Hate it when I get into math trouble. Take the 54,000. That's what we came up when we used 1.20 at 54,000. So that's 20%. That's 0.20. So let's take 64,800 times 0.20. That's still not doing what I want it to do. I'm sorry, 64,800 times. Now I'm going backwards the other way, so I go 0.2. It keeps giving me a figure I don't like. I'm trying to prove this, but I'm having a hard time. If I increase anything by 20%, I'm going to increase it by 1.20. So we're going to go from 54,000 to 64,800. Let's see what the difference is. 64800 minus 54,000 equals 10,800. Now that's the figure I'm wondering why I'm not coming to. That's the difference. That's the additional weight. Now it gave us, when we take 1.20, it gave us 64,800. But when we just take 20% of 64,800, we'll come up with 10,800 pounds. So that is the additional weight that you would have to consider when you're thinking of how long it's going to take you, and that 64,800. I'm talking 64,800. You would add 10. You would be adding 10,000 to the 54. So that's what makes it 64,800. And that's what you would consider when calculating your fuel mileage or fuel per hour, ever how you do it in your company. In this situation, it's probably fuel per hour, because hours are the key in heavy equipment operations. Now we have a sort of understanding of this rolling resistance deal. Let's go on down here. So let me find where was I? Digging resistance, we talked about that. We talked about soil conditions that affect the machine. Rolling resistance, digging resistance, tracting. We talked about rolling resistance. We went through a calculation to determine what we would use as total weight. So 20%, let's read this. The effect of a rolling resistance of 20% as if the vehicle is towing an additional 20% of equipment and has higher excavation costs. It may be necessary to use a ripper attachment to help with the excavation, a ripper. Now, this is talking about digging. I'm not going to. This right here should go up to digging resistance. All material has some degree of resistance to excavation. Some materials have more resistance than others. The type of material, along with its hardness, cohesiveness, Weight and degree of compaction determines its resistance. Naturally, more resistant material requires heavier duty. Where did that go? Heavy duty equipment and has higher excavation costs. This is digging resistance still. It may be necessary to use a ripper, and now it makes sense, attachments to help with the excavation. And we all know what a ripper is, I hope. And there is one if you don't. It rips up the soil, and then you can doze it easier because it breaks it up. The material's resistance must be established before excavation starts so the proper equipment can be selected. Typically, excavation is divided into 3 categories: rock, hard digging, and easy digging. Rock is generally solid, that's hard. And it's going to say rock is generally hard. And over here, it can be broken along the fissures. Like when you get to rock, if it's not solid, it may have cracks in it and it may have fissures. It may be lapping each other. And you want to dig against those overlaps. It makes it easier digging. And that's what they're talking about, coming from different angles with the equipment. Often rock can be broken by excavating beneath it and allowing the weight to shear off pieces of rock. Now the vehicles approaching the rock mass, the vehicle, where sometimes rocks have been formed with fissures that can be broken along fissures approaching the rock mass from a different angle. Now moving on down, particles can be dangerous, although this practice, pieces of rock, this practice can be dangerous. The vehicle, some of the things where is that going? Can be dangerous. Some material can be broken mechanically with a pneumatic machine called a jackhammer. Hard digging doesn't require drilling and blasting, but some easy digging materials. You can read these things. I don't think that they throw this in here and they don't talk much about it, but I want to bring it up. By the way, you will need to reread this. I'm sure you figured that out by now because it kind of bounces around. It just throws this in here. Equipment weight distribution. Equipment weight distribution refers to the force of an engine's power on the drive wheels. Torque. Drink of water. Some of the things that affect vehicle traction, I don't know where this started. We went through the different, here we go, traction. Traction is the friction between the road surface and the tire or tracks of the vehicle. Low friction between the road surface and vehicle tires allows the tire to spin. That's when we're in mud, snow, and ice, without moving the vehicle, forcing some of the engine power to be used to overcome the spinning of the tires rather than to move. So you're spinning your wheels. That's not where the saying came from, I don't think, but perhaps it is. So easy digging materials are usually, where did the world did traction go? Here we go. Allows the tires to spin, used to overcome the spin, and so we're spinning our wheel. Rather than to move the vehicle. Some of the things that affect vehicle traction are the surface material. That's what we've been over, the mud versus the sand versus the asphalt and things like that. Are the surface material. Now it throws in a big fancy word here, which is actually beyond the scope even of NCCER. But let's read what it says. We can look up the coefficient, but it's a complicated formula. It's physics, by the way, dynamics. Some of the things that affect vehicle tractions are the surface material, coefficient of traction, the weight of the vehicle, and the type of tires or track. And then it just leaves it. It leaves us hanging. But let's finish reading it. You can look this up if you want to, and you'll see that it's a physics calculation, and it's not easy. It'll be using symbols and things like that. But there's an actual coefficient of friction, and it's a factor that you use over and over again, depending on the situation. Equipment weight distribution. Equipment weight distribution refers to the force of an engine's power on the drive wheels of a vehicle. Engine power on the drive wheels of a vehicle moves the vehicle across a surface. Ideally, all of the engine's power would be used to move the vehicle instead of other things because of traction and rolling resistance. The coefficient of traction and the amount of weight on the vehicle's drive wheels determine the amount of force a vehicle can deliver before the tires start to slip. Now that thing is doable, but it's beyond the scope of NCCER, and it's beyond the scope of our goals. Look it up. Feel free to mess with it. We're not going to do it because it's well above our level and our needs. Another point, though, to keep in mind is that when climbing a hill, gravity shifts some of the vehicle's weight to the rear wheels, thus increasing traction for rear drive vehicles. Unfortunately, when driving down a steep grade, gravity shifts the vehicle weight to the front wheel, thus decreasing traction of the rear drive vehicles, which can make a vehicle difficult to handle. But let me tell you something right here. This is a free tip. If you're an excavator and you're going up sandy loam, a pile of sandy loam, that weight's going to shift to the rear. Now, maybe you can put your bucket in front and that'll help a little bit, but what's going to happen is since you're in sandy loam and most, if not all of the weight has shifted to the rear, your rear drive sprockets are going to just dig into the dirt and you're going to have a hard time getting anywhere. You may help a little bit by shifting, rotating your cab to where the cab is facing to the rear, but it's best to have the sprocket, in other words, the differential or the drive system in going up first. And that way you're pulling yourself up that hill instead of pushing yourself. There's a huge difference in that when it comes to traction. The weight on the rear now won't matter because the only thing on the rear is the idlers. Your drive sprocket is in front of you now, so the weight going to the rear is not going to make any difference. Another point to keep in mind is that when climbing a hill, gravity shifts the vehicle weight. We just unfortunately when driving down shifted, but you get the point. Tire treads and traction. Tire treads are the working surface of a tire. The type of tread helps determine the flotation capacity of the vehicle. Many tires are designed to work effectively in many different environmental conditions. Generally, tires with a deep tread provide good traction under most conditions, but shallower treads are best on dry sand and ice because of surface contact, because they have better flotation. They keep you above. For tires to operate correctly, the operator needs to be sure that they're inflated according to this. Now, this is the pneumatic tool that I talked about for busting up rock. This is a throw in here, and it just is their little, let's talk about trenching a little bit, but I don't think it's wet clay and loam slab off. Sandy soil collapses. Firm clay and loams crack this is all true, by the way, and fall on you. And that's bad since it's dry clay because it's extremely heavy. Wet sands and gravels tend to slide. I don't think that's on a test, but you may want to go through this review. And if you keep on going, you'll have an excellent summary. I recommend you go through that. It's a summary of the whole module, not just this section. And to see how you've done so far, I would suggest that you see how you do on this. Airspace or open pockets between soil particles are called what? Voids, right? Which of these factors has the most effect on the classification of soil? Size of particles has the most factor. We've talked about that. Which of the following soil types has the finest grain? Silts and clays. We've talked about that. Fine sand would be your correct answer. The grain size of the soil. I don't know why I'm doing this, but it's a good little review while we're here. The grain size of particle soil. I'll let you try to do this, and it'd be a good study, be a good review. This is over everything we've covered thus far from section 1, section 2, and now section 3. When we get into, which is in week 4. Now, let's turn our attention to what's just been standing over here waiting on me to quit fumbling around and trying to find my way to this ill-structured module section over here. Blame it on that. Here we have, let me see if I can do something with this. Can I? No? I know I can. There, I did. So here we have week 4 when we get here. You'll know when we're here because we'll be here. This is where I'm going to put the video. Read this because the way I had to go through this, it'll be better if you go back through it and read it. Go through that summary and those review questions, and it'll bring you up to where we are actually when we get into the midterm. It'll be a good prep for the midterm. So I'm going to suggest that you go back through that. I wish I could insist because it'll really help you with the midterm when we get there, which will be week 5, which is, well, from here, not long, but from the starting point is 5 weeks. There is a tailgate in here that I think is well put together. If it's the tailgate, I think it is. Ooh, I like this video, and then it's going to ask you to talk about some specific things in here. Really do like this video. It's good on sizes of particles and things like that. So I'm glad that's there. Can I sneak back? I did. Now, the thing I'm interested in, and from that module, there will be a quiz over it. I don't think it'll be very long. I think we could sneak in here and see. This is old test. Can I sneak in here without going through? Yeah. It's got how many questions? 5 questions. Goodness, that's just putting water tires. This is going to be a whiz for you right here. Track vehicles performed on muddy ground can be improved by. Oh, yeah. You'll do quite well with this. Let me see if I can get back to the little bit more intense. The reading material. Now, this assignment, I think I have it written down, and so I will read it. Let's see if I can help this. Oh, yeah, I can. Right? What else can I do? let's leave it right there. I think you can handle it. Now let me read this. In section 3.2.1, rolling resistance, and section 3.1.1, this is all in the instructions for the week 4 assignment. Weight bearing. Familiarize yourself with table 8, weight bearing capabilities. We did that. And table 9, rolling resistance percentages. We did that. In the problem requiring the use of table 9, assume the vehicle or machine is equipped with radial tires. That would help you with the percent thing, which we talked about. You remember that, and round the percentage off? I think we used 2%, and the factor would be 1.2 to get what the total weight would really be like. But round your percentages off, and then here's the 2 questions in here. Your total points here are 100 points. So guess what each question is worth? Suppose you have a fully loaded 10-wheel dump truck. That's how many wheels, weighing 13 tons, driving on clean, dry sand. Your contact area of each tire surface is 104 square inches. That sounds familiar. Per tire. Remember, how many tires do you have? It's a 10-wheeler. Remember, you are looking for pounds per square inch. Refer to table 8 to determine if there will be a problem. Now, let's see. Let me get my self kind of situated here. So let's take this in steps. So it's just saying, will there be a problem? In other words, at some point, we're going to have to go to a table and see, we're going to come up with some pounds per square inch here. And we're going to see if the road bearing capacity will handle that. I wonder if I could find table 8 real quick. I think I can jump around here a little bit. That's the rolling resistance. There we go. So, can I move you a little bit? No. But I can do this. So let me read this. This is what you're going to be doing. You might want to take notes when you go through this. The total surface area is 100. I'm working on this problem right here. Right? So where does it say? No, that's not a problem. I'm working on this one right here. So this is going to require the load-bearing capacity chart. Suppose you have a fully loaded 10-wheel dump truck weighing 13 tons, driving on clean, dry sand. Your contact area of each tire is 104 square inches per tire. And remember, you're looking for pounds per square inch. Refer to table 8 to determine if there is a problem. Well, table 8 shows us here the different things. We're clean, dry sand, so we got to have something in the problem. We are fully loaded 10-wheel driver on clean, dry sand. So we're going to have to find something that will stay atop of the bearing capacity of clean, dry sand, which is 27 pounds per square inch. So let's see what we come up with. Back here, with the surface for each tire has 104. Remember, you are looking for pounds per square inch, so refer to Table 8 to determine if there's a problem. So let's talk ourselves through this. The total surface area is 104 square inches per tire times 10 tires. That's 1,040 square inches, by the way. So the where's the dump truck? Fully loaded dump. The dump truck weighs 13 tons. So how many pounds is 13 tons? Well, you got to multiply 13 times 2,000. That means 26,000 pounds is the total weight. And what do you do with that total weight? You divide it by the total square inches of 1,040. So that area multiplied by 13 tons, which is, we need pounds, 2,000 pounds per ton, is 26,000 pounds. So when we take 26,000 pounds and divide it by 1,040, because remember there's 10 wheels, we're going to get 25 pounds per square inch. Now, over here, it says the best I can do, guys, is 27. So we came up with 25 psi per square inch. That's what we have. Now, what the load-bearing capacity is 27 pounds per square inch. So we just barely, there's not a problem, but do you want to cut it that close? Could we not just change the tires on it before we even start? See, this kind of stuff is figured before the job starts, by the way, in the estimating portion of it. So a little bit bigger tire would probably kick us up, so we'd be in safer territory. But, you know, according to this, we have 25,000 pounds per square inch. That's taking the total square inches of tires surface area, which is all the tires, and the weight of machine. Weight of machine divided by total area, which is 1,040 square inches. Maybe safe, but I would just go at it with a little bit bigger tire, I think, or I feel like, or I would certainly recommend. Now, so that takes care of that problem. What's next? You need to maneuver a fully loaded scraper weighing 27 tons. So we got the weight of a fully loaded scraper weighing 27 tons. Well, that's 54,000 pounds, by gollies, with radial tires across a very soft, muddy, rutted roadway with 12 inches of penetration, no flexing. In other words, the road's kind of solid. In terms of fuel consumption, how much additional weight would we have? So let's go back to this surface area. That means we got to go to Table 9. So bear with me while I find Table 9, which should be kind of close. I just saw it referred to. Now, let's find that surface area. Right, very soft, muddy, rutted roadway, 12 inches of penetration, no flexing. That's what we have. And if we have a radial tire, they don't care. They're both the same. So we have 20%. So we would have to take, where is it? The 54,000 multiplied times 1.20, and that would give us 64,800 pounds. That's an additional load of 10,800 pounds. So we would have to calculate our fuel and our production time based on carrying a load of 64,800, when in reality we only have machine and all 54,000 pounds, machine and all. But we had to do our calculation as if we were carrying a load of 64,800. And I got that by using the table, multiplying it times the where is it? The 27 tons, which is 54,000. And that gave me a total of 64,800, which is an increase of 10,800 pounds. So what we would have to base our estimation for fuel consumption and production time on, it would be as if the machine, the payload, and the rolling resistance would be, we would have to base that on 64,800 pounds total for doing our calculation. Thank you for bearing with me. Thank you for me searching around over here, taking the time out. I believe that this might help you. How did that do that? I believe that going through this might help you. Move this over. And so I'm just going to stop right here and see you next time.